Let's take a look at how the energy changes that occur in phase changes. So remember, we have different phases. We have the solid state, the liquid state, and the gas or vapor. And so we have words that we use when we're talking about going between. Solids going to liquids are called melting. And because you have to add heat to melt something, that's considered an endothermic process. Now the opposite, if a liquid goes to a solid, we call that freezing. And in order to freeze something, you have to remove heat. So that is an exothermic process. The amount of heat that needs to be added or removed can be calculated with a constant that's specific for each substance called the heat of fusion. The heat of fusion is a number that tells us how much energy it takes to either melt or freeze 1 gram of a specific substance. Remember, the number would be the same for melting and freezing. The difference is when you melt something, you have to put energy in, and when you freeze something, you have to take that much energy out. Now going to the next, so that's going from solids and liquids. But we can also go back and forth between liquids and gases. So a liquid to a gas is called vaporization. And to vaporize something, it requires energy. So that's an endothermic process. A gas back to a liquid requires the removal of energy. We call that condensation, and because it removes energy, that's considered exothermic. The amount of energy it takes to vaporize vaporize something, or that has to be removed to condense something, is called the heat of vaporization. And like the heat of fusion, that number depends on the substance you're talking about. But you would have to add that energy in to vaporize it, or remove that much energy out to condense a substance. We also have something that you may or may not be familiar with, and that's the possibility of going between solids and gases without going through a liquid state. So this is not very usual at atmospheric pressures, but two substances that do. One is mothballs, which you may be familiar with, and the second one is dry ice. So if you ever go to the grocery store and get dry ice, you'll notice that goes directly from a solid to a vapor. It's solid carbon dioxide, and it goes from a solid to that gas in a process called sublimation. That requires energy, so the sublimation is endothermic. You have to put energy in. Now, if you could remove that much energy, you could go back from a back from a gas to a solid. That's called deposition, and you have to remove energy to do that. So understand, going between different phase changes, you have to go for, if the phase, in terms of energy, remember this. The solid has the least amount of energy. And it's partly kinetic energy, right? And then you have a liquid, which would have more than a solid. And then we have gases, which, remember, is moving very quickly, and this has the most energy. I'll just put E for energy. So if we're thinking about it, endothermic and exothermic, when you go from the least to the most, these you're adding energy, and so all of these processes are endothermic. Right? Solid to a liquid, liquid to a gas. You have to add energy. When you want to go the other way, so if you want to go from the gas, which has the most energy, back to the solid, which has the least energy, see, you're getting less energy, so you have to remove energy, and that way is exothermic. So if you think about it that way, you'll recognize that going from a solid to a liquid and a liquid to a gas are all endothermic, or going from a solid to a gas. You have to go from least to most energy. But going from the most energy of a gas back to a liquid or a solid is exothermic because you have to remove energy. Now there's a really cool diagram called a heating curve. And this heating curve is my sketch, and it's for water. You can see here. And there's a couple reasons I really, really like this. So in a heating curve, you have the x-axis right here, and that just represents the heat that you're adding. And then you have your y-axis right here, and that represents the temperature, and as you go up the axis, the temperature is getting higher. Now on a heating curve, there's two important temperatures. This one is the boiling point, because we're doing water. And the 100 degrees is the, This is the, let me get it back. Sorry, I didn't catch what I was saying. This is the melting point for water, 0 degrees, and 100 is the boiling point. Now those are the two important temperatures, and let me walk through this graph with you. I think it's fun. So all a heating curve is basically watching the temperature as you add heat and melt the substance, or add heat and change the phase in the substance. So you start somewhere below the melting point, and so if you're below the melting point, you would be a solid. Once you hit the melting point, what you see, and this is what I think is so cool, is that the temperature stops changing. And you get this plateau. So you start right here as a solid, but if you're at the melting point and you're adding heat, eventually you're going to turn into a liquid. So by the time you get to this part of the line, you're a liquid. So all along this line, what's happening is melting. And you have this plateau, and in between, you would have not just solid and liquid, but solid and liquid. So then once you completely change into a liquid, then you see that the temperature goes up. And now you have a liquid that's just heating up. This is normally what we see when we're trying to boil water in lab for something, and we just watch the temperature go up and up and up. Once you get to this boiling point, see right up here, you notice again that the curve plateaus. It becomes flat. Now right here at the beginning, you would just have a liquid, but the vapor would start coming, and as you're changing the liquid into gas, the temperature stays the same. That's why if you ever were cooking and you wanted pasta, once it boils, it's going to stay at the same temperature until all the liquid's gone. Because as long as there's water in there, the temperature will remain the same, even if you're adding heat. Now once you get to the end of the line, you have gas only, and then now we're just warming up the gas here. So the thing that I think is so interesting for you to understand and look and think about here are those plateaus. How the temperature does not change at the melting point or the boiling point until the phase change is complete. So as long as there's two phases present, even if you're adding heat, the temperature remains the same.